Hello everyone and welcome to our ECC 2021 presentation, Co-Design of Autonomous Systems from Hardware Selection to Control Synthesis. My name is Zardini and this is a joint work with Andrea Censi and Professor Emilio Frazzoli. This work is sponsored by ETH Zurich and the Swiss National Science Foundation through NCCR Automation. This work addresses some of the pain related to the engineering of complex systems. If you think about it, the design of an autonomous robot involves many different building blocks, such as perception, control, planning, energetics, and communication. These components range from hardware to software, and having a good understanding of the whole system is very difficult. In particular, we lack a formal theory to optimally co-design heterogeneous systems. In this work, we tackled this issue by proposing a co-design framework which allows one to embed the synthesis of controllers into the co-design of the whole autonomous robot. The proposed approach is very intuitive and allows for rich modeling capabilities, including analytic models, catalogs, and simulations. Furthermore, the compositionality and modularity of the framework allow interdisciplinary collaboration and provide actionable information for designers to reason about their problems. The proposed approach is based on a monotone theory of co-design, which defines a design problem through three spaces. First, the implementation space, which represents the design choices, the options we have. Second, the functionality space, which represents our objectives, what we need to achieve. And finally, the requirement space, which describes the resources we need to provide the functionalities. Typically, you can understand functionalities as something you want to maximize, and resources as something you want to minimize. In this framework, we model both spaces as partially ordered sets. Since this is not a common concept, let's first define partially ordered sets. A partially ordered set is a set P together with a partial order, which is defined as a reflexive, transitive, and antisymmetric relation. A typical example of partially ordered sets used in design are total orders. For instance, you might describe your energetic cost with the ordered positive reals, or the number of robots in your fleet with the ordered natural numbers. However, posets give you a lot more flexibility than total orders. For instance, in this work we will use a partial order on positive semi-definite matrices. Consider two such matrices. First of all, we know that such matrices have real eigenvalues and can be therefore graphically understood as ellipsoids. We can define an order given by ellipsoid inclusion. A matrix A precedes a matrix B in the partial order if and only if B minus A is again a positive semi-definite matrix. In other words, A precedes B if the ellipsoid representing the matrix B contains the ellipsoid representing the matrix A. Now, given the knowledge of posets, we can formally define design problems with implementation. These are composed by the functionalities and resources posets, F and R, the implementation space, I, and two maps, prov and rec, mapping an implementation to the functionality it provides and the resources it requires. We represent design problem with implementation with the following formal graphical notation. Functionalities are green continuous wires on the left, and resources are dashed red wires on the right. Implementations are hidden. Think, for instance, about the design problem of a battery. Functionalities are the capacity and the maximal provided current, and resources are the cost and the mass. Implementations, instead, are the different battery models which you can find on the market. Now, for the purpose of design, we need to know how something is done. However, for the algorithmic solution of co-design problems, we will forget for a moment about implementations and focus on feasibility relations. A feasibility relation is a map from the product of the functionality space with inverter ordered and resources to bool, the poset containing only the elements false and true. Each pair of functionalities and resources is mapped to true if there exists an implementation providing at least the requested functionality, requiring at most the proposed resources. This is a monotone map, since lowering the functionalities will not require more resources, and increasing the resources will not provide less functionalities. The cool thing about feasibility relations is that we can compose them together in many ways. When composing design problems in series, the semantics is that the resources required by a first design problem are provided by a second design problem. Furthermore, we can have design problems in parallel, and we can model feedback when resources are fed back to become functionalities again. Finally, we can choose between two options, or ask two design problems to hold at the same time. Interestingly, design problems are closed under composition, meaning that any of the mentioned compositions will return a design problem. This is a very useful tool when decomposing large problems into smaller subproblems, and will be very important when co-designing a whole robot. Now, given a composed co-design problem, there are two main queries we want to answer. First, by fixing the desired functionality, we want to find design choices minimizing the needed resources. Dually, we can fix the resources we can spend and maximizes the functionalities we can get. In both cases, we can retrieve the optimal design solutions. We will now focus on the first query. Technically, we are looking for a map H from the functionality space F to the upper set of feasible resources. Practically, this will be a map from the functionality space to anti-chains of minimal resources. We won't go into the details of the optimization, but we want to notice that the described query gives a family of optimization problems in which you have a functionality chosen by the user and you want to minimize the needed resources. Such problems are a particular case of multi-objective optimization problems, which are not convex or differentiable, not continuous, and not even defined on continuous spaces. Now, given the map H for each design problem composing a bigger co-design problem, we can recursively find a map H for the entire diagram, relying on the different composition operators. The minimal set of resources can be obtained as a least fixed point of a monotone map in the space of anti-chains. The introduced tools are now useful to describe the main result of this work. In this complex diagram, you find the co-design problem of an autonomous robot. The formulation provided in this work allows us to include the design of a controller, which you see on the left, into the design problem of the whole system. We instantiate the reasoning for the case of LQG control and provide modeling results for both the continuous and the discrete time cases. For the continuous time case, we consider standard stochastic dynamics with Brownian processes on the system and on the observations. We consider the classic infinite horizon LQG problem and recall the optimal control law, relying on the solution of two Riccati equations, one for the control and one for the estimation. Now, how is this useful to think about the control problem as a design problem? First, we split the usual LQG performance metrics describing tracking error and control effort. We call the new metrics ptrack and peffort. Given this separation, we are now ready to state the first result of this work, which simply says that we can write the LQG problem as a design problem with observation noise and system noise as functionalities and tracking error and control effort as resources. The monotone relation between the two is intuitive, and you can see this from the figure on the right. Being robust to higher observation and system noises will require equal or higher tracking error and control effort. We can prove this formally in 4 steps, using the partial order on matrices defined before. First, we rewrite the performance metrics in explicit form, noticing that they depend on the solution of a particular Lyapunov equation. Second, we show the monotonicity of tracking error and control effort with respect to the weighting matrices Q and R for the LQG problem. Third, we show monotonicity of the solution of the Riccati equation for estimation with respect to the noise covariances V and W. Finally, we can show monotonicity of the performance metrics with respect to the noise covariances. This result can be further extended. First, while staying in the continuous time domain, we can assume observation and computation delays, and we can embed them in the LQG design problems, bisecting them as functionalities. This can be done following what we call the substitution principle. In the case a certain nuisance is lower, or in other words, less impactful on the system, the controller can artificially simulate an higher nuisance. In this particular case, if I have small delays, I can very easily simulate higher ones. Now, these results can be generalized to the discrete time case, in which we consider a sampling process, a discrete LQG controller, and a zero-order old integration. In such systems, we possibly lose observations, and we model this via the so-called dropping probability. With this new setting, we can write the LQG problem as a design problem very similar to the previous ones, now including the dropping probability as a functionality. Proving this result requires methodologies very similar to the previous ones, and you will find them on the paper. Now, why did we do all of this? Well, given these results, we can naturally include the design of a controller, which is a very formal thing, into the co-design problem of a robot, which, given sensor measurements, needs to reach specific targets in space at specific times. This design problem involves more practical things, such as the choices of the batteries and of the sensors to be put on the robot, as well as the implementation of specific algorithms. Let's have a quick look at this co-design diagram. Block number 1 represents the LQG problem, and the implementations are given by the solution of LQG problems for different parameters. Information to the control block is given by a feature extractor, which can be implemented by different algorithms, and which receives measurements from a vision sensor. The implementations for the latter are catalog of sensors. The objectives of the control action are dictated by a mission planning block, which lets the user choose the number of missions the drone has to accomplish and the time they need to last. Based on this information, actuators, batteries, and computer units need to be chosen from catalogs, and algorithms need to be implemented. Finally, you can notice how we are able to sum common resources, such as computation, costs, power, and mass, and how they contribute to the feedback loops, which represent the irreducible complexity of such co-design problems. Now, the interconnection of all these design problems forms a co-design problem, which we can solve with the introduced tools. We can then code these models with a formal language, which is very intuitive to use, and we can solve them using the MCDP solver. We now look at the kind of solutions we can produce. By fixing some functionalities, here the number of missions and the mission time, we can produce Pareto fronts of solutions in terms of tracking error, power consumptions, and costs. Given the complexity of the problem, we are not interested in providing a single optimal solution, but rather an informative anti-chain of optimal ones. For instance, you can notice that in order to achieve low tracking error, you will need to spend more energy and more money, and given these trade-offs, the user can decide where to stop on the curve. Second, you can see that for each optimal solution, we can characterize the heterogeneous design choices by listing the chosen computer, the frequency and the details of the controller, the chosen battery, actuators, and sensors. Finally, I care about showing you the monotonicity graphically. In this picture, you can notice how increasing the desired functionalities, here again the number of missions and the duration of the missions, we can obtain dominating upper sets of feasible solutions. Now, what are the takeaways? First, I've shown you that using co-design, it is very easy to embed the synthesis of controllers, here we used variations of LQG control problems, into the co-design problem of the whole autonomous robot. Second, I've shown you that this is a very intuitive modeling approach that does not require acrobatics like common in optimization theory. This framework comes with an interpreter and a solver, which allows to easily model problems of interest. Through the co-design of an autonomous robot, we discovered the rich modeling capabilities of co-design, including simulation-based, catalogs, and analytical-based models. Even if we did all of these models, this framework allows multiple users to co-design a system altogether, promoting interdisciplinarity. Finally, I gave you a taste of the kind of questions we can answer with this framework and the kind of actionable information we can produce for autonomous robots developers. Now, of course, this is just the first step, and this is a very new theory. We would like in the future to showcase compositionality by including the co-design problem of this robot into the co-design problem of a fleet of robots. Second, we would like to generalize this modeling approach to other control structures, which include nonlinear controllers and also receding horizon controllers. Finally, we would like to exploit this framework to synthesize energy and computation-aware control strategies by exploding the models representing computation, energetics, and control. This is a new topic, and we are really in the middle of the evangelization process. This includes writing a book, teaching classes, both at ETH and internationally, and organizing international workshops. You can find more information at the listed pages. Thank you very much.